what if a robot could learn new skills not from some tedious line-by-line code, but from just browsing the internet? Well, that's the incredible promise of a new AI model from Google DeepMind called RT-2, and it really looks like it could completely change the game for how robots learn and interact with our world.
So to really get why this is such a huge deal, let's just start with this one mind-blowing example. A robot is told, "I need to hammer a nail." Simple enough, right? But there's no hammer around. So what does it do? It looks around, sees a rock, figures out it'll do the job, and picks it up. Now that's not just following a command. That's improvisation. That's actual reason.
And that, right there, is the million-dollar question we're going to dig into. How on earth does a machine make that conceptual leap from the word hammer to the physical object rock? Well, the answer lies in building a bridge between two totally different worlds of learning, the physical and the digital.
To really appreciate this new breakthrough, we first have to understand the old way of doing things. For decades, teaching a robot any new skill has been this incredibly slow, painstaking process. And honestly, it's created a massive bottleneck for the entire field.
This really lays out the core problem, what you could call the fundamental data gap in robotics. On one side, you've got traditional robot learning. It's slow, it's super expensive, and it's all based on physical trial and error. And on the other side, you've got the internet. It's got a vast, almost infinite amount of data, and learning from it is fast and cheap.
And when we say vast, the scale is just staggering. Our best AI models are trained on billions, literally billions, of images and chunks of text from the web. It's an amount of data that's just physically impossible to collect with robots in the real world, at least not anytime soon.
So we've had this massive ocean of abstract knowledge from the internet on one side, and on the other, we have our robots that need to do very specific, concrete things in the real world. The challenge has always been, how do you build a bridge between the two?
And this is where the brilliant, kind of simple insight behind RT-2 comes into play. The researchers realized they didn't need some super complex, fancy bridge. They just needed to teach the AI a brand new language, the language of action.
Now, the tech at the heart of all this is called a vision language model, or a VLM. The easiest way to think about it is like an AI that has spent its entire life just absorbing the internet. It's seen billions of pictures, it's read trillions of words, so it's gotten incredibly good at looking at the world and just talking about what it sees.
So RT-2 basically uses one of these VLMs as its brain. The robot's camera shows it the world, and it gets a command in plain English. The VLM takes all that in and uses its massive web knowledge to figure out what to do. But here's the magic trick. Instead of replying with words, it spits out a special action sentence. It's basically a string of text that directly translates into the robot's physical movements. Think of it like learning a new vocabulary, where the phrase "move your arm to these coordinates and close the gripper" just becomes a single word for the AI to learn.
And hey, don't just take my word for it. The researchers themselves put it perfectly. They literally express the robot's actions as text tokens. A super complex physical movement is treated exactly the same as any other word in a sentence. The model learns to speak action just like it learned to speak English. This whole approach unlocks this really critical training method they call co-fine-tuning. By mixing the robot's real-world training data with all that original web data, the model learns about abstract ideas and physical actions all at the same time. And this is so crucial because it stops the model from forgetting all that powerful knowledge it got from the internet in the first place.
Okay, so that's the theory, but the real question is, does any of this actually work in the real world? Well, the results are, and I'm not exaggerating here, nothing short of remarkable. This new method unlocks all these incredible new skills that they call emergent abilities.
Let's just look at the numbers for a second. This chart shows how well the robot does in situations it's never seen before. New objects, different backgrounds, you name it. The previous best model, RT-1, only got it right about 32% of the time. RT-2, it hits 62%. We're not talking about a small improvement here. It's nearly double the performance. That is a massive leap forward. And this incredible jump in being able to handle new things is what leads to those emergent abilities we were talking about. These are skills that just kind of appear, not because anyone programmed them in, but because the robot now understands the world on this much deeper semantic level, all thanks to that web data.
So check this out. This robot was never physically taught what the letter X means, or what the German flag is. But its brain, the VLM, has seen those symbols millions of times online.
So when you tell it to move the banana to Germany, it just gets it. It connects that abstract symbol to a physical action.
And honestly, it gets even more impressive. The robot can understand a request to move an apple to a Denver Nuggets logo, or a Coke can to a picture of Taylor Swift. This shows a level of semantic, even cultural understanding that is it's way beyond what traditional robotics could ever do.
And we can put numbers to this, on these new emergent skills, things involving symbols and reasoning. The old model had about a 17% success rate. RT-2 is over 3 times better, at almost 60%. I mean, just pause on that for a second. That kind of jump is the difference between a robot being a frustrating toy and one that could actually start to be genuinely helpful.
And this brings us right back to where we started, with our rock and our nail. Using a cool technique called chain of thought, the researchers can actually peek inside the robot's thought process. You give it the command to hammer a nail, and the model first thinks to itself and writes out the word rocks, identifying the right tool. And only then does it generate the action command to go and pick one up. It's wild.
Okay, so let's zoom out and look at the big picture for a second. Why is this whole co-training idea such a potential game changer for the future of robotics? What does this all really mean?
Well, it really feels like a paradigm shift. First, it means we can now plug these huge, general-purpose AI brains directly into a robot's body. Second, this creates a direct pipeline for all that knowledge on the internet to flow into the physical world through a robot. And third, it unlocks that emergent reasoning, letting robots solve problems in ways we never explicitly taught them. But here's the real kicker, the most important takeaway from all of this. It means that robotics doesn't have to exist in its own little bubble anymore. Every single time our general AI models get smarter or faster, our robots can inherit that intelligence almost instantly. The two fields are now tied together at the hip.
This research really kicks open the door to a fascinating future, and it leaves us with a pretty powerful question to think about. If a robot can learn from the sum of all human knowledge on the internet, what's going to be the first truly helpful general-purpose robot we actually invite into our homes? And how is it going to change our lives?